Having seen a few expressions, let's write a function. And we're going to do this using the design recipe. We happen to be using racket. This idea of the design recipe is steps you use when you're writing any function. You've probably maybe followed these steps before in other programs you've written without maybe realizing you were following some steps, and you might have done them in an order that ended up giving you some bugs later on by doing it in maybe a non-optimal order. So, to write a function, we're going to follow the 4 steps of the design recipe, which are highlighted here. So, for every function we write, we're going to first write some unit tests. And we do this first, before the code. Then we're going to go ahead, and most of our time talking about this. Grading will give a big chunk of the points to this, maybe up to half the points just for your good unit tests. Then we'll go ahead and write the signature, the purpose statement, and stub out the function. Finally, we'll go ahead and complete the body of the function. And then hopefully everything should work then. So those are the 4 steps we're going to follow. Let's work through an example, and we'll come back and talk more about the details of these steps as we do them. So we'll write a function pizza area. Not a dramatic function, but you walk into a pizza parlor, you know how much the 14-inch costs, you know how much the 18-inch costs, maybe you don't want to know which is a better deal, you just want to know how much pizza you're actually getting for your money. So yeah, if you have an 18-inch pizza, I went ahead and pulled out my calculator and thought about it, scratched my head, drew a little sketch, an 18-inch pizza, and I had to remember the area of a circle, so the radius is 9 inches, and I plugged it out and found out that the area of a 18-inch pizza is 254.5 square inches. Okay, so this is my first test case. Okay, and it's actually, I'm going to call my function pizza area, and remember that this is a function call, and it should return that value. Let's write some more examples, some more unit tests than that. And I have up here knee-jerk things you should consider. They don't always apply to every problem you write, but you should at least think of them automatically. So, for functions, if it takes in numbers, think about taking in 0, taking in 1, taking in a big number, many. If you're writing a function that takes in a string, think about a string of length 0, a string of length 1, a string of length many. If you're writing a function that takes in a list or an array, think about a list or an array of size 0, 1, or many. And test each of those, write a unit test that includes each of those cases. If we're dealing with numbers, again, maybe fractional numbers, negative numbers, and maybe think about having some examples of that. So, let's go back and say, hey, I have one example for pizza area here. Let's make some more. Check expect. This is something built into the racket language. In Java, you have to import JUnit to get assert equals, so you have to put it inside a class and do some extra overhead. Check expect built into racket, very nice to the student languages. So what's another thing we should try besides 18? Now, a lot of people will say, well, what about a 14-inch pizza? And they'll pull out a calculator. And what about a 20-inch pizza? Those are all good things to try, but remember what we just said? Let's see if we can apply that thinking. 0, 1, or many. Well, let's start with 0. So, pizza area of 0. Okay, well now, that's kind of silly, right? Who's going to order a 0-inch diameter pizza? Should that be maybe an error? Should we sort of say that, hey, 0 is not a valid input? Should we say that in this case we should throw an exception, or maybe return instead of returning a number, return a string saying bad input? And I'm going to go ahead and posit a little software engineering principle saying, if the answer is, I don't know why somebody would ask about a 0-inch diameter pizza, but if they do, I can tell you what the area is. It's going to be 0, right? There's no doubt about that. And so I'm going to say, if the answer is good, don't have our code forbid people from asking it. We'll give the correct answer. Why they ask it, that's their business. We might have some higher level logic in our program that controls what sort of pizzas people ask about. But if they do ask about a valid pizza size, pizza area will give it to you. And we don't care what a valid pizza size is. as long as we can get the right answer. So, yeah, so 0. How about check expect of pizza area of 1? Now remember, we're thinking 0, 1, and many. 18 is a many. We already have sort of this example now of many. So let's test 0. 1 is, okay, in this example, 1 is kind of tough. I'm going to have to pull out my calculator. Can we think of an example where I don't need to pull out my calculator? What's another number? Maybe not 1. Some clever people might have thought 2. If I have a 2-inch diameter pizza, then the radius is 1 inch. Pi times 1 squared. I can square 1 in my head, and I can multiply by 1 in my head pretty easily. So, yeah, this is going to be 3.14, approximately. This is maybe an inexact number. I should probably put a inexact up here and an inexact here. So hash I is racket's designation of an inexact number that corresponds to a double in Java. Great. So yeah, this is good. In fact, if I wanted to, we saw we had the placeholder pi. We could use that as well. Yeah. So these are my examples of 0, 1, and many. And I'm happy with that. I don't need more. Don't go ahead and say pizza area of 14 and pizza area of 23 and all that. If you want to do a bigger one, check expect one that I actually throw in another one I can do entirely in my head. When I ask for a test case, or a unit test, I'm not asking you to do a whole lot of work and a whole lot of pulling out calculator and scratch work on the side. Make it as simple as you can. So another one where I can go ahead and do it in my head. Multiplying by 1 was easy. Multiply by 1. Multiply by some other perfect square? Oh, by 100. Yeah, I'll bet if I have a 110 squared, 20. But if I have a 20-inch diameter pizza, then a radius of 10 inches and pi times 10 squared, yeah, that's going to be 314, something like that. Okay. Yeah, so, oops, a hash I for inexact. And if you want, some people want to do this. Some people want to say, hey, could I go ahead and say, hey, times pi 100? Sure, I'm fine with that. Either way, both of those are good answers. In fact, this one here, this test case is already giving me something that I might have ending up in my code. I'm starting to actually write the function already here in my test cases. That's fine. Okay, so 0, 1, many. This function pizza area doesn't handle strings or lists or arrays, so I'm not going to worry about that. Fractions and negatives. Can I take in a fraction? Like two, so I'm thinking like 2.5 when I say fraction, a non-integer. Yeah, I can order a 2.5 square inch pizza. I guess. I've never seen that on a menu before, but hey, why not? Maybe we're doing something, we're taking our pizza sizes that were given in centimeters and converting them to inches for our function or something like that. So no sweat, no problem. Yeah, let's have one test case that includes fractional numbers. Is there a fractional number that works well here? Gosh, that's a little bit tougher. If I go ahead and take 2.5, then yeah, I'll go ahead and gosh, I think it's going to be pi times 1.25 squared, 25/16. Oh man, okay, yeah. So how about this? Yeah, I'm happy with that. Yeah. So okay, great. So this gives us a good set of tests. Oh, and then negative numbers. Okay, so negative 10-inch pizza. Ooh. Okay, now 0, I couldn't see why somebody would ask that, but I knew the answer. Negative 10, that doesn't even make sense to me as a question. What is a negative 10-inch diameter pizza? I'm thinking right now I need to say in my, the my function has to take in a real number, and it can be a non-negative real number. It can't be negative, okay? So I'm not going to worry about a test case for a negative number because I'm going to let you know that I'm going to write that in my contract. Can't take in a negative value. Do I need to worry about a test case where you, instead of passing in a number, you pass in the string aloha? No. No, we're going to say that this function takes in a number, and we don't need to test things that aren't even valid types of input. Okay, so that is a few more tests. We're going to come back. There's going to be a couple little glitches here dealing with inexact numbers. We're going to have to come back and address, but that gives us step 4, writing our unit tests. Awesome. Okay, step 5, signature, purpose statements, stub out the function. What do we mean by all this? So signature, here's what I'm going to write, define, and this is going to be the syntax for writing a function. Define pizza area. We saw how to define placeholders before, identifiers. Define n to be 17, something like that. So this is going to be, let me get this up here so I'm looking more closer to the camera. Define pizza area, and now we're going to list our parameter name. What's a good parameter name for what this function should take in? It takes in a number, so I'll say that, but so should I call it num, or number, or real? Yeah, those are all somewhat descriptive of what's coming in, but is there a more descriptive thing, something that actually describes the meaning of that number? I know it's a number. What's the meaning of the number? Ah, it's the diameter of the pizza. So use a good variable name, use good parameter names, okay? Diameter, I don't care if you spell out diameter. In fact, if you just use D, we're so used to D as something we use in our math books that I think D is actually a good descriptive name. We'll have a comment in a second here. Okay, let's go ahead and put in a purpose statement. Return the area of a pizza with diameter inches. Okay, so return the area of a pizza. Here's another tip to think of, especially when you're working with the real-world units, real-world numbers. What are the units associated with them? If there are units associated, then let me know. So I'll say, hey, this is the diameter in inches, and I'm going to return the area in square inches. Okay. So let me know the types of what's coming into the types of what's going out. And that should be mentioned somewhere. It shouldn't just be in your head invisibly. Now, agreed. For this example, if I use centimeters, my answer will be in square centimeters, and it's going to be the exact same code. So whether it's inches or centimeters or any unit, doesn't really matter. I could just say of a certain length. But I want you to get thinking about, hey, tell me what units you're expecting. If you're giving a temperature, tell me if it's at Celsius or Fahrenheit or Kelvin or whatever. So, okay, this is the purpose statement. This might well call the header. The one other thing I want is the signature. Remember what the signature is? We talked about those last time. The types that come in and the type that we return. Okay, so what type comes into this thing here? It takes in, and I'll remind us that when we saw signatures last time, we said we're going to write them like this, with an arrow and the type that comes in and the type that goes out. We're going to use this prefix notation even for signatures. We're going to use it everywhere in racket, be nice and uniform. Okay, yeah, so it takes in Java, I'd say double, okay? But here we decided it wasn't any double, right? It had to be a non-negative double. So we're going to actually go ahead and say that, non-negative. In racket, we call them reals, and they can it can be a double or an int. It can be an exact or an inexact in racket. So, okay, we'll say non-negative real. And what type does it return? Again, in Java, I just say double. And the fact that it's non-negative in Java, I would have to go ahead and put that in my comment and say, hey, the inputs must be non-negative. That's an extra constraint that wasn't in the type system anywhere. Non-negative real. The answer will also be it could be 0. We had that test case involving 0. 0 could come in and 0 might go out. But it will never be negative. The area will never be negative, and the input diameter will never be negative. Okay. So we go ahead and have this right now. And we can put this in a comment here. And the last thing I want to do is stub the function. What is a stub? A stub is writing as much of the function as I need so that it compiles and runs, but it's going to fail all the test cases, just about, right? Why? Because I'm not actually computing the answer. I'm just returning 17. I'm going to do something that does match the contract. 17 is a non-negative real, so I'm happy about that. So at this point, I'm going to now run my program. We have a bunch of test cases, and we have a program that has its, let's look at here. We did the signature, the types. We wrote the purpose statement in a comment, and we stubbed out the function, made it so it actually runs. Okay, so let's go ahead and run that. Running right here is good. It will catch any errors we have with parentheses if we got those wrong. It's also going to catch a little glitch about some of these numbers, I believe. But yeah, so I'll go ahead and run this. And it says, ooh, check expect cannot compare inexact numbers. So another thing we talked about last time, that don't compare doubles with equals. Instead, use some function that takes in two doubles and tells if they're really close to each other. Just like you don't compare, in Java you learn don't compare strings with equals, but they never really tell you don't compare doubles with equals, but it's true, don't. And in JUnit, yeah, they actually have assert equals that takes in two doubles to see if two doubles, a test like this test that we're doing here, they actually take in three things in JUnit. It takes in the two doubles you want to compare and a tolerance of how close is considered good enough. 0.1, 0.0001, smaller or bigger. We're going to do the same thing here. With our check expect, we're going to go instead of, so check expect cannot compare inexact numbers, try, and the error message here actually goes in habit, try check within, and then the test, and then our number, 254.5, and then the range, the tolerance. Okay, that's the typical term for that. Okay, so check within, and I want to be within 0.01. Okay, call that good enough. Okay, so actually my answer here, well, yeah, 254.5. How accurate is that? I did it on my calculator and I just wrote down the first few digits. So that's probably within 0.1, maybe even within 0.05. Yeah, so there, that's a good tolerance for this example. And this is good. However, we're going to have the same problem here. Check expect of pizza area of 2 should be pi. That's going to be a check within. Pi is a double. And so, yeah, we want to do that with 0, 0, 0. In fact, when I say that, so I'm going to make these with check within, so ones they have doubles show up in them. And the double shows up in the output, but, actually the input is kind of a little bit inexact as well, right? Like when I order a 2-inch diameter pizza, it's exactly 2 inches. If I take it into a physics lab and get the laser measurements and all, it's exactly 2 inches in diameter. Nah, it's close to 2 inches, but it's not exact. So, really I should sort of say that input of 2 inches was really an inexact number. Not only is the result going to be an inexact number, but if I'm really thinking closely about types, and why are we programming if we're not thinking about types, right? Yeah, so let's go ahead and do that. By the way, noticing in Java, if you said this 20.0, that would turn an int into a double, okay, and it would be inexact by nature. I think we saw in Racket that 20.0 is exactly the same as 20, because it can keep track of rational numbers exactly. So we really want to say hash I if we have something like that. And then these are actually going to be inexact as well if you really want to get pedantic about it. But, again, I could probably leave those off. The fact that I'm multiplying an inexact number like pi means this entire result is going to be, by Racket, inexact. And you say how close is good enough. And I think that's something like that is good all around. Okay. The fact that I gave the answer is like 100 times pi, I already know that, yeah, that's actually a whole bunch of decimal places going on in there. So if I had said, let me leave it like this, backtrack on this one, I'll say, yeah, the answer should have been 3.14, 100 times that, 314.159. There we are. And that should be within point, yeah, one. So yeah, I think that's good to that many decimal places. So, okay, this now is a good set of tests. You're like, yo, Barland, you missed one, right? Line 24, we didn't make that inexact. Yeah, I'm going to go ahead and 0, I'm going to maybe say it's going to be an exact number. Okay, I can roll out a 0-inch diameter pizza pretty accurately because here it is right there. I kept any dough all away from it, so I know it couldn't be a fraction more dough than necessary. Okay, now let's go ahead and run this. And so again, where are we? We are on, we did step 4, then we did step 5, and you're like, yeah. But it actually made us reconsider things about step 4. Running it made us think about inexact numbers for this particular example. A lot of examples won't deal with inexact numbers. A lot of examples on other programs will involve strings, okay, or things like that. So, but this one happens to be numbers. And what do we get? We get a window of test results and sure enough, check failures. The actual value 17 is not within 0.05 of the expected value, etc., etc., etc. Okay, good. We expected that. We thought that would happen. We knew that we hadn't finished yet. Okay. So now, and something I should mention about when writing unit tests is, I say put in the expected answer. I mean, put in the correct answer to the problem. Okay. Even if you know that you're going to write code that's going to be a little bit wrong, or that initially it's going to be a little bit wrong, don't put in something just to get your test cases to pass. Even though it's not the correct answer, your unit test should have the correct answer. And you want to know, you might go ahead and ship your product with some knowns like, hey, we don't pass all our tests, we're a little bit off in certain cases, but at least you know about that. If all your unit tests pass, your manager is going to say, hey, all your code is correct, and we don't need to put any caveats in any of our anything we put out about our program. It's all working correctly, and you've now fooled your boss, and they will not be happy when they find out that you'd been fooling them. So, for unit tests, put in what the correct answer is. I'll say what the expected answer is, but I don't mean, hey, I know my code is going to do it this way, and so it's going to give this answer, and so that's what I'm expecting to happen. Really should be the correct answer. Okay. Check expect, check within. I'm going to leave that one as check expect because we're using exact numbers. Okay. Now we get to go ahead and put in the actual body function. This is step 7 of the design recipe. And now that we've done this, we've actually thought about it in writing the unit tests. Realize that to say this is a diameter, we need to cut it in half and square that and multiply it by pi. How do we multiply something by pi? Oh yeah, we remember that from our building up our expression. Something times pi, and this is going to be the radius squared, which is going to be half the diameter squared. That's half the diameter. Okay, I need that squared. And there's a couple things we can do here. We can go ahead and call a function that squares it. Like in Java, you might call math.pow. If you just want to go ahead and write the same thing again, I'm fine with that. We're going to multiply these 3 things. This, the pi, the radius, and the radius. And I'm fine with that. There is a function sqr that will square. So sqrt is a square root, and sqr squares something. You could use that as well. Let's go ahead and run this. All 5 tests passed, and that means we can go on to the last step of the design recipe, which is that. Woohoo! Okay, so in the functions you write, go through these steps, go through them in this order, and think about the unit tests, okay? We're really going to give grading consideration to having good unit tests. I don't need a lot of them. A 0, 1, many kind of covers all this. This is We have the 0. We have something close to a 1 case, something that I didn't need any calculator for. One that I did need a calculator for. So, and then one with a fractional number. I thought that was going to make sure we don't do anything. We're not calling some built-in library that doesn't accept fractional numbers. You can imagine maybe if our math.power didn't allow fractionals, or we had some bug like that, we'd want a test case that caught the bug. Okay. So yeah, this is, probably, so this was maybe not even necessary. This would be more than enough test cases for what I'm looking for in this class. Okay. One last thing. And this is pretty cool here. The types here, we put this signature in, and right now I wrote it as a comment. Oops. Okay. It turns out we can make that real. We can actually have that checked in real time. Okay. We don't use define to do that. We use define/contract. Okay. Define/contract. Actually, let's undo this just for a second, and I'm going to go back and ask you, given one example, can we extrapolate the general syntax for calling a function? What is brackets syntax for calling a function? And again, as an example, what am I asking for? In Java, it's something like object, and then a dot, and then a method name, and then an open paren, and then a bunch of expressions. I use ... to say, hey, a bunch of 0 or more expressions. Yeah, so again, this replaces some particular object, but the dot has to literally be there. If there's not a dot there, you're not calling a method in Java. Ish. Java has multiple syntaxes for things, and one that can admit that if your object is this. Anyway, yeah, so that's what I'm asking for. So that's the syntax in Java. What's the syntax in Racket for calling a function? And we saw several examples here, and I've seen lots of examples. Oh, I didn't want calling a function. I wanted defining a function. Well, this is good review too. In Racket, we decided it was open paren, and then function name, and then the inputs that it wants. There. In Racket. Okay, but here's what I wanted to ask is, what's the syntax for defining a function? Racket syntax for defining a function. I'm not even going to try to give the Java for that because it's more involved, but in Racket, defining a function, we say open paren define, open paren define, open paren function name. In Racket, I guess we say function hyphen name. We don't use camel case idiomatically. Okay. Define function name, and then you don't have several expressions. You have parameter names. So we have, as one of our technical terms in programming languages, a parameter. A parameter is a local variable that you have in your function, and it gets initialized when the function is called later on. So, okay, so here our parameter, we only had one, and it was called diam. You can probably guess if you have multiple parameters, you put them all here. What is a parameter as far as Racket goes? Any identifier. Okay, so define function name there, and then we can go ahead and have, what do we have? One single expression. That is the answer that gets returned. We don't say the code word return like you do in Java, and we can only have one thing there. Only one answer can come back from a function. So we're going to have one expression, not like 5 statements followed by a return statement like you would in Java. Okay, so great. That's our syntax for defining a function. I like putting in the purpose statement there in a comment, but that's not part of the syntax, so I won't put it in part of the syntax. But I will say now that if we want to, we can make this real. Now we're going back to what I started a moment ago. We can actually put this contract here in for real and say define/contract. So it's not, the keyword's not defined, it's define contract if you have two things following. So, or define function name identifiers, 0 or more of them, 1 or more. Actually, it will be 1 or more in our student languages that we're using. So we could say define /contract, and then we put some particular contract. And what does the contract look like? The contract looks like this, followed by a predicate of the input types, and finally a predicate for the return type, and then an expression. And what is a predicate? Okay. Again, a predicate is going to be a function that returns a Boolean. I'm going to leave it at that as far as the syntax level here. So there are two versions of define going on: define and define contract. Define has one thing, the expression to return, one thing in the body of the function. Define contract has two things in the body: the contract and the expression that's going to get returned. Okay, and we run, and now it says again all 5 tests pass. And here's the interesting thing, just so you can show that define contract really checks its stuff. I'm going to go ahead and try calling pizza area not with 10 or something like that. I'm going to go ahead and call pizza area with the string hello, and we get the message pizza area expects a non-negative real given hello. Okay, and how about pizza area of -23? And you can see that again, we don't need to provide our own check expects that passed in different types or things that didn't meet the contract. Defined contract will do that for us. And if our code didn't return the correct type, it will go ahead and also give an error. Here it actually says who to blame. It's blaming, well, it's this Dr. Racket top level window here. However, if the input types are correct and the result type didn't meet this criterion, then at runtime we would get the error message saying broken contract, blaming the function at line 38. So that's kind of cool. Okay. In class, we'll go over some more examples of this and let you try your hand at it as well.